Hey, thanks again for joining me. And we're going to talk about the anatomy of an atom. So, what exactly is an atom? So, an atom is pretty darn small, actually. So, it is about 10 to the minus 10 of a meter across. So, these are important numbers to sort of keep in the back of your mind. The mass is exceptionally small, somewhere on the order of 10 to the minus 23 of a gram. So these things are really, really tiny. In fact, if I take, normally I do this with a piece of chalk on the board, but if I take a line and maybe the pen or a pencil or something that you've written on a sheet of paper, and I draw a line across the paper like that, it is about 3 million atoms wide. So these things are so tiny that even a very thin line is made up of 3 million atoms in width. So incredibly small. We can talk about the anatomy of an atom. It's actually made up of three different things, and let me go ahead and start a new slide here. So the three components are protons and electrons, and it turns out that all atoms have these. And the last thing is that of a neutron. And it turns out that pretty much every atom but one has a neutron inside of it. And so, what are these things? So, these protons have positive charge. So, I'm going to write plus VE for positive because I am exceptionally lazy. So, this means positive charge. Electrons have a, oops, sorry about that, they have a negative charge. So, I'm going to write minus VE for negative. So the VE is the VE at the end of the word, and the minus and the plus is for negative or positive. So a negative charge. And neutrons actually have no charge at all. So you've probably seen the joke, maybe. Maybe I'll look up the joke. So a neutron walks into a bar and asks, "How much for a beer?" The bartender replies, "For you, no charge." It's a very corny joke, I'm sorry. I will promptly delete it and we will pretend you never saw that again. So protons have a positive charge, electrons are negative, so exactly equal and opposite, and neutrons have no charge whatsoever. In terms of masses, the proton has a mass of 1.67 times 10 to the minus 24 of a gram. A neutron has almost exactly the same charge to mass, to three significant figures. It's identical, but if you take it out a digit or two more, it's slightly different. 1.67 times 10 to the minus 24 of a gram. And electrons are about 2,000 times lighter. They are 9.1 times 10 to the minus 28 of a gram. So very small compared to a proton or a neutron. But all these masses are pretty small anyway. In fact, normally what we do, right, is we invent the atomic mass unit as a way to avoid writing these incredibly small things. So 1 atomic mass unit, or 1 AMU, or 1U for unified unit, we define as 1.67 times 10 to the minus 24 for the gram. So what do we have here? We have a proton, which has a mass of 1.67 times 10 to the minus 24 of a gram. That's 1 atomic mass unit. The same for a neutron. And the electron, it's about 2,000th of an atomic mass unit. But what we're going to do is we're going to say, for all intents and purposes, it has no mass at all. So you'd have to have 2,000 electrons to have the mass of one proton or one neutron. And no atom's going to have more than 118 electrons. So it doesn't even come close to weighing the same as a proton or a neutron. So we're going to ignore it. And if we go ahead and we look at at a drawing of an atom, so that is a very poorly drawn atom, what we find is in the center, and that's actually a little bit larger than it should be, but I'm going to go ahead and make it even larger still, is a place that we call the nucleus. And the nucleus is where you find protons and neutrons. In fact, I'm going to go ahead and write protons as a P plus and neutrons as an N0, just to remind us of the charge. And the atom itself, we said, is approximately 10 to the minus 10 meter wide. The nucleus itself is about 10 to the minus 14 or so of a meter across. So you're looking at about 10,000 times smaller. And the standard analogy is, if the atom is the size of a football field, the nucleus is about the size of a grape in the center. So it's exceptionally small. So I really shouldn't have drawn it that large, but otherwise you really can't see it. In fact, nucleus comes from the old word meaning nut. So it's a very hard, dense region. So you can see that the protons and neutrons have all the mass, and they are essentially inside of this nucleus. And that fluffy electron, right, I'm going to go ahead and just kind of draw that electron out. There's kind of a cloud of electrons. They kind of flit around, and we won't say too much about that, but they kind of flit around. So you've got an electron cloud, so I'll write E minus for electron cloud. That's nice and fluffy, and 99.99% of the mass is in the nucleus, so almost all of the mass is in the nucleus. So that fluffy, light electron cloud on the outside has almost none of the mass of the atom. And so that's the anatomy of an atom. So that's nice. There's not too many complicated Latin words to learn here, unlike regular anatomy, but that is our knowledge of the atom, or at least this will be fine for our chemistry course. So this now brings us on to the idea of atomic number. So what makes an element an element? So what is the difference between carbon and gold or oxygen, right? So what is it that makes an atom of carbon different from an atom of gold, different from an atom of oxygen? And the answer is the atomic number. The atomic number we normally give the symbol Z to. And it turns out that it is the number of protons in the nucleus that determines what kind of element we have. So for instance, carbon has an atomic number of 6. So carbon atoms are anything that contains 6 protons in their nucleus. It doesn't matter what else they have. If they've got 6 protons, they are called carbon. Oxygen has an atomic number of 8, which is to say it's got 8 protons in its nucleus. And gold has an atomic number of 79. So that means that gold atoms have 79 protons in their nucleus. And if we compare that to something like lead, lead has an atomic number of 82, so 82 protons. So actually, we can turn lead into gold if there was some way to remove 3 of those protons. So we could actually change lead into gold using the Philosopher's Stone, which, if you've read Harry Potter, is the title of the first book. Actually, it was called the Harry Potter and the Philosopher's Stone in England, but it was called Harry Potter and the Sorcerer's Stone in the States because people thought incorrectly that philosophy was boring, so no one would want to read about this stone that could remove, presumably, those 3 protons and change lead into gold. So how do you actually know this, right? So how do you know gold's got 79 protons inside? Well, if you go to the periodic table and you know your element symbols, you'll know that gold has a symbol of AU, and right above it is written a number, and that number is 79, and that is the atomic number. And below it is written a number, and I have a very small periodic table that I'm staring at right now, and underneath it, it says 197.0. And we'll see in a minute that that is something to do with the weight of the atom. But go ahead and find lead on your periodic table, and again, you will have PB for lead, and you'll have above it written 82, and below it, if I squint at my itty-bitty, I got a pocket-sized periodic table, my lead is coming in at 207.2. So the average weight of a lead atom we'll see is 207.2 atomic mass units. But that 82 up above and that 79 is how we determine what we've got. So go ahead and, just for fun, potassium. So go ahead and look up on your periodic table and tell me the atomic number of potassium, which of course is the number of protons. So go ahead and pause and find potassium, and we'll check our answers. Okay, if you're unpaused, potassium is one of those squirrely elements that has a symbol K. And if you look at potassium on the periodic table, it's got a number 19 written above it. So that means that potassium has 19 protons. So its atomic number is 19. And that means that anytime you got 19 protons inside your nucleus, then you've got a potassium atom. All right, thanks for watching. And let's move on to another video.